Welcome to the Rocket Propulsion Masterclass. In this week's episode 3, things are really starting to get interesting, so I'm not going to hold you back for very long. Let's get right into the course.
Now, so far we've only talked about energy, mass flow, perfect gases and so on. Now, another great law of mechanics is momentum. Where does the thrust come from? Well, we are going to put the propellant into the chamber at very low velocity, and it's going to come out of the nozzle at very high velocity.
Right.
Therefore, there's been a huge change of momentum. Mass times velocity is the momentum, and therefore we've got mass flow going in with very low velocity. We've got mass flow coming out, same mass flow, but now with very high velocity, and that produces a force acting on the nozzle. If we integrated all of the pressure forces acting on the nozzle wall, that would be equal to the momentum of the exhaust jet.
Okay.
Now that's very convenient because integrating the pressures all along the combustion chamber contour would be very difficult, whereas simply multiplying the exhaust velocity by the mass flow is very easy.
Right.
But we know from Isaac Newton that that will equal the forces acting on the combustion chamber, and that makes our life an awful lot simpler.
So if you know the momentum of the exhaust jet, it's easy to figure out the momentum of the vehicle.
Exactly. I don't know a single rocket engineer that's ever worked out the thrust by integrating the force along the nozzle contour, although quite a lot of rocket nozzle computer programs do actually do that. And when it comes to calculating something called the thrust coefficient, which we'll come to in a moment, then we'll talk about that. So, well, let's talk about the thrust coefficient now. If we can finish up with a calculation of something called the thrust coefficient, multiply that by the combustion chamber pressure and the throat area, that's another way of getting the thrust on the nozzle.
Okay.
But we need to know what the thrust coefficient is. And George Sutton in this book tells you how to calculate the thrust coefficient for a one-dimensional nozzle.
Oh, so a nozzle where you hang on, one dimension, so no sides, no depth.
So all that's happening is that all the flow, remember, is in a parallel direction. There's no divergence of the flow.
Oh, so it assumes basically a perfect exhaust jet.
Exactly, it's a perfect exhaust jet, and by the time we've got to equation 331, then we've calculated a thrust coefficient.
So you just take that and you multiply it by what you expect the efficiency of the engine to be. So would that be like 0.9,
Well,
0.95?
we'll come to that in a moment. By the time we get to the end of this, we'll talk about thrust coefficient efficiencies. But the next question is, how big has the hole in the throat got to be to pass a given mass flow?
Right.
So we've got, we're feeding in a certain amount of propellant. Our feed system dictates how much propellant is going to go into the combustion chamber in kilograms a second. We know that that's going to burn with a certain pressure and temperature.
Right.
How big has the hole got to be now?
Because if it's too small, the pressure won't be able to force it through the throat fast enough.
Absolutely.
And if it's too big, you won't get a high enough efficiency because it won't accelerate at a high rate.
So we come up with something called the characteristic velocity.
Okay.
And the characteristic velocity is very, very simple. It's the throat area times the chamber pressure divided by the mass flow.
Okay.
And there's a calculation that you can do to get that for an ideal gas, and then very conveniently, if you can't be bothered to do the calculation, George Sutton presents you with some very nice graphs that you can sort of stick your pencil on and find out what numbers you want. So we've got to the point then with a couple of coefficients, the thrust coefficient and the characteristic velocity, that given a combustion chamber, if we know what pressure we want to operate and what temperature, and we know what mass flow, we can calculate the size of the throat, and then we can calculate what the thrust coefficient is for a given area ratio. So what we now come to is a problem where we've got a rocket engine, a nozzle, actually operating in the atmosphere. So this could be anything from sea level to the vacuum of space. Might be an altitude of 10 kilometers, but there's a pressure acting on the back of the nozzle from the atmosphere.
Right, because I mean, unless you put a boat tail around it, as some rockets do, you're going to have atmospheric drag over the engine belt.
Yes, so remember that the flow inside the nozzle is supersonic, and therefore the actual condition in the nozzle is determined by the area ratio of the nozzle. And so the nozzle knows nothing about what's going on outside, because remember that pressure can't travel upstream in the supersonic part. So the flow inside the nozzle is determined entirely by what you make the nozzle. So you can have a huge nozzle, you can have really, really low pressures inside the nozzle, and the flow would reach very high velocities.
So that means, like, no matter what the atmospheric conditions, no matter what the atmosphere is doing to the exhaust jet, it can never mess up the interior of the engine.
Right, now that would be what would happen if, remember that I laid some emphasis on we've got the boundary layer.
Oh, right.
And so what happens in a real nozzle is that we could have a nozzle running at sea level, and the pressure inside the nozzle might be 0.8 of an atmosphere and 1 atmosphere outside. Happy nozzle, that will work.
Okay.
And so we might make the area ratio a bit bigger, and so the flow now expands to 0.6 of an atmosphere, and it's still quite happy. But by the time we get to 0.4 of an atmosphere, something known as the Summerfield criterion, remember the atmosphere is pushing on this boundary layer.
So do we get flow separation where the...
Precisely, absolutely in one go. At round about 0.4 of an atmosphere, the boundary layer is now so fed up, it peels off the wall, and therefore the flow now concentrates itself towards the centre of the nozzle, and the atmosphere has caused the flow to come away from the wall in that location.
So you get a nozzle, and the gases, instead of going all the way down the wall, they sort of peel off at that point.
That's correct.
And so you get an area of, like, outside atmosphere being pocketed there.
Yes, so if you imagine a nozzle, what happens is the flow is stuck to the nozzle walls down to this point where you've reached 0.4 of an atmosphere, and then it's come off and it's forming a jet down the centre of the nozzle, and then there's a little recirculation of gas actually in this region between that jet and the nozzle wall, and so that doesn't run full. That's roughly at atmospheric pressure, and the bit in the centre is roughly at 0.4 of an atmosphere.
And that's very bad, I presume.
It may or may not be. So
I suppose it depends how robust the nozzle is.
So it depends on whether it's stable as well.
Right.
So one of the problems that you get is unstable separation, and the stability of the separation depends very much on what the actual shape of the nozzle wall is. We've talked about bell nozzles. If you've got an absolutely straight conical nozzle, then the separation can actually be stable, provided that the angle of the wall is quite low, around about 10 degrees. But rocket nozzles tend to be around about 15 degrees to keep the weight down, to keep them short and to keep the weight down.
Right.
And that flow separation can in fact be unstable. And what happens if you imagine there's the nozzle and there's the plane, then you get a wobbling of that separation plane. And of course, as it wobbles, the pressure on this side of the nozzle is different to the pressure on this side of the nozzle. Remember, we said that you've got 1 atmosphere where the flow's separated, 0.4 of an atmosphere where it hasn't, and so that generates very large side loads on the nozzle, and so that shakes the engine about. And you try to make nozzles as light as you can, and that flow separation can very quickly destroy a nozzle.
Right.
So what you would like to do is to avoid flow separation if you can at sea level.
So make engine nozzles at sea level have low expansion ratios, where the throat is closer to the area of the exhaust.
So try not to go down to 0.4 of an atmosphere or below. Try to stay at around about 0.45 or something like that, so that the nozzle just runs, and then there's no separation in the nozzle. What happens is, as the high velocity low pressure flow meets the outside atmosphere, a shock wave forms in the exhaust.
Okay.
And if you look at rocket nozzles, you actually see this rather better in the reheat ducts of fighter aircraft, because they've got a lot of kerosene in them. The kerosene and the soot glows and illuminates the exhaust rather nicely. And you'll see there are some rocket propellants where you can see this quite clearly. Hydrogen oxygen engines tend to be very transparent, but liquid oxygen and kerosene engines you can tend to see it in, and you will see coming from the lip of a nozzle a shock wave, and then that reflects from the centre and you get shock diamonds in the exhaust.
Shock diamonds, like
Yeah.
what one was it? Was it the Delta 4, the Delta 4 Heavy that is famous for those?
It could be, yeah. I'm not particularly familiar with the
Okay.
Delta 4 heavy
Yeah.
exhaust, but on typical rocket engines you will see
It might be a different vehicle, I forget exactly, but one of the rockets is famous for having prominent
if
shock
you look
diamonds.
at the Russian Proton rocket launch, for example, that has a highly visible shock diamonds in the exhaust.
Okay.
What I've just said about separation is not necessarily universally true. Depending on what the shape and the nozzle exit angle is, you can put up with some separation. And in fact, on the early Atlas missile, the first generation of Atlas missiles, the core engine actually ran separated at sea level.
Well, that would make sense. The Atlas is a really peculiar rocket because the booster engines drop off mid-flight, which means the main engine has to be efficient enough to work very well in a vacuum.
So
which
that
means
central engine had an area ratio of about 25,
Okay.
and they did achieve a situation.
25 is high enough to achieve flow separation.
And the pressures that were being used in those days,
Oh,
yes.
okay. I presume it changes based on engine
Yeah,
pressure.
so back in those days, we were very lucky if we could get up to 40 bar chamber pressure. Nowadays, of course, rocket engines run at 200 bar or even higher.
Right.
So things have changed a lot in terms of the technology. But when by the time we've got to page 67, figure 3.8, George Sutton discusses the flow separation problem quite a lot, and then the next illustration, figure 3.9, he goes into what the thrust coefficient of a separated nozzle might be. Okay, because obviously when the flow separates, it changes the thrust coefficient, and he's got some nice sketches as we go on through figure 3.10.
Right.
And so on.
Okay, so we think that's a good place to pause. We're going to stop here and pick it up the exact same place next week. In the meantime, make sure you write all of your questions down in the comment section and we'll see if we can get around to answering them in future installments. See you next time.